In this video, we're going to look at Unit 5, Lesson 10 for Algebra 1, which is looking at rates of change. In the warm-up, it says that let P be a function that gives the cost, P of T, in dollars, of producing 1 watt of solar energy, T years after 1977. So on the next card, you're going to get a table showing you the values of P from 1977 to 1987. And you want to just come up with at least one thing that you notice and one thing that you wonder. So pause the screen and write down one thing you notice and one thing you wonder in your workbook, and then come back to the video. Certainly lots of things you could notice and wonder here. One thing maybe you noticed was these values of the wattage. So it's saying to produce, or the cost, sorry, the cost of producing 1 watt. So here, from here to here, it changes. It goes down 20, right? And then from 60 to 45, that's down 15. And then from 45 to 33.75, it's down 11.25. And then you could look again here, 33.75, down to 25.31, and you'll see it's lower than 11 again, and it just kind of keeps going down, right? So when you get down to the last one between 9 and 10 years after 1977, then we see that it's only decreased by 1.5. So maybe you're noticing that the amount of change is decreasing over time, and certainly plenty, and maybe you wondered why that is. Why isn't it staying the same? Or certainly a ton of other things you could have noticed and wondered as well. So then go ahead and finish the rest of the warm-up. So figure out which expression represents the average rate of change in solar cost between 1977 and 1987. And you can pause the video to give yourself time to think here. So we're looking at 1977, which is the first year that this table started, right? So that's 1977. And then 1987 is 10 years later. So that's this year here, this data point here. So remember, when we're finding average rate of change, we want the cost per unit of time in this case, okay? So our P of T is cost. So we're wanting cost per unit of time, okay? So per year here. So we want the average cost per year. So we're looking at taking these values, the cost values, and subtracting them. And you always want to do the new cost minus the old cost, okay? So you're taking new minus the original, which I like to call the OG. And the way that we do the cost is with the function notation, right? That P of 10, P of 0. So we see that this number 1 is subtracting those, and we see that number 3 is subtracting those, but 2 isn't, nor is 4. And so now that would just give us the change over the 10 years, right? But then we want this to be change per year. So then we have to take and divide this by the time period, right? So how many years happened in here? And so then that's going to be 10 minus 0. Now, in this case, just 10, right? Because 10 minus 0 is just 10. But if we're thinking about this in terms of if the first starting year wasn't a 0, if we had done it to year 4, we would be doing 10 minus 4. So you want to do the change in the cost over the time period. So number 3 there. So the different values in each expression and what they represent in context. So remember, we had our function notation. So when we looked at P of 10, this is a cost, and then T represented 10 years, after 1977. So you could say it like that, or you could just say the cost in 1987. So if you didn't want to say it like that, you would do 1977 plus 10, and you could just say the cost in 1987. And then is the price increasing or decreasing each year? And it's decreasing because it's less, right? So the price was going down. We saw it going from 80 down to 60, down to 45, right? So that price is decreasing because the numbers are going down. In this next activity, you're going to be investigating some stuff to do with coffee shops. You're going to be looking at the average rate of change for a couple different time periods. You're going to answer some more questions, and then you're going to discuss the reasoning that you used to answer the questions. So here's a graph that shows the number of coffee shops worldwide that a company had in its first 10 years between 1987 and 1997. A table with the same information is going to appear on the next slide. The growth in the number of stores is roughly exponential. So when we look at this graph, remember that you read a graph like you read a book. So as we're reading these sentences, we're reading from left to right. Okay, so you're going to read a book a graph from left to right as well. So we can see if we were going to be connecting these points, that they're increasing from left to right. So as your eyes follow this way, what are the dots doing? And they are going up. So we can kind of see that increase there. One other thing that you may notice, right? They said roughly exponential. That's because it's going up at a steeper rate as we go on over time, right? Versus linear functions that you looked at go at a constant rate, meaning that they would be able to be connected by a straight line. And these points we can't connect with a straight line. We get that curve there. So number one asks you to find the average rate of change for each time period and then show your reasoning. So again, you can pause the video and then try this and then come back and see the work for it. So for part A, I'm just going to do this in blue down here. Okay, so for part A, you want to do the average rate of change. So remember that this is going to be the new minus the original, and then over the time period is kind of a thought process there. And you want the new output, right? The new cost, or in this case, the new number of stores. So we're going to be doing did they give us a function name for this? No. Okay. So I'm just going to do F for function. So we'd be doing F of 1990 minus F of 1987 divided by the time period, right? So those inputs. So 1990 minus 1987. That's the idea there. So the number of coffee shops in 1990 is 84. The number of coffee shops in 1987 is 17. And then we'd be doing 1990 minus 1987 was over a 3-year period. So when we divide this down, we end up with 22.333 repeating. So there's a change in increasing the stores 22 1/3 or 22.33 repeating stores per year. Next one, okay, we do the 1993 number of stores, right? So the top is going to be your number of stores. So 1993 is 272. Whoops. And then 1987 is 17. So 272 minus 17. And then on the bottom, we would do 1993 minus 1987, the number of years in that period, and that's 6 years. And when we divide that down, we're going to get 42.5. So then in that time period, we increased the number of stores by 42.5 stores per year, right? So we can say stores per year. That's what we're finding here. And then this third time period, so now we're looking at 1997, which is 1412. There was 1,412 stores. 1987, 17. And then in this case, from 87 to 97 is 10 years, in a 10-year period. So the change in the number of stores divided by 10, and this is going to give us 139.5 stores per year. So that's a significant increase in that one. So in the first 3 years, increasing by 22 1/3. The first 6 years, 42.5, and the first 10 years, 139.5 stores per year. Number 2 says to make some observations about the rates of change you calculated. Do these average rates tell us how the company was growing during this time period? So I just made a couple observations, right? So that first 3 years, okay, so in the first 3 years, right, it was 22.33. And then in the first 6 years, it was 42.5 stores per year. And then in the first 10 years, it was, what was it? 139.5. Whoops, I changed these colors on accident. Okay, so 139.5. So the average rate of change of the first 6 years, right? So in these first 6 years versus the first 3 years, that almost doubled. And then the average rate of change in the first 10-year period, so if we did 139 divided by 22, that's like 140 divided by 20 almost. So this is 2 times bigger. Well, in the first 10 years, it's 7 times bigger, meaning that the company increased its number of stores or started doing a lot better in those first 10 years, right? So it was slower in the beginning adding stores, and then they started adding quite a bit more as time went on. 3, use the graph to support your answers to these questions. How well do the average rates of change describe the growth in the company in the first 3 years, 6 years, and the entire 10 years? So when I do this, I kind of look at, if you want to be looking at the graph, so average rate of change, I connect the 2 points that we were looking at, okay? So the first 3 years, we were looking at the first year and then the third year. So that's year 0, 1, 2, 3. So we kind of we looked at those two. So then I like to think about connecting those. If you have a ruler or something, you can connect these and just extend it. So you can see it does an okay job in the beginning, right? So it kind of almost hits the first 4 points, and the 5th point is just slightly above it. So if you were predicting, this would be a good predictor within the first like 5 years. And this started in 1987, right? So this would be good till about 1992. And then the first 6 years, so this one, we looked at the first 6 years, so year 1, 1, 2, or year 0, and the first year, right? The starting point, and then 1, 2, 3, 4, 5, 6. So then again, I would connect this and just kind of look at what that line does, since average rate of change is really like a linear look. So it's okay, right? These dots are all below it, so it's over predicting in the beginning, but it's still not like very high above those dots. So you're not way off, but then doesn't like way under represents these dots, because these number of stores are way above that average rate of change line. So if you started predicting with this average rate of change, 10 years, right, you're going to end up here, which is way less than 1,400, right? You're way under 500. So it over predicts here, okay, and it under predicts here. So not great. Then for the first 6 years, or sorry, for the entire 10 years, so now you've got this one and you've got this one. And those were the two dots you used to calculate the average rate of change. So now when we look at this, I mean, it doesn't predict the growth at all, right? These are so far below that line. And then the 10 obviously is right on it, but that one is really not a good predictor at all of what's happening with the number of stores. So then let F be the function. So that represents the number of stores, T, years since 1987. They're telling us now that F of 20 is 15,011. Find F of 20 minus F of 10 divided by 20 minus 10 and say what it tells us about the change in the number of stores. So they're giving us this new F of 20 value is 1511, right? So 15,011. So that's going in here for F of 20. And then we're going to subtract F of 10, which was the number of stores 10 years in, which we know from the table is 1,412 because it's the 1997 value. And then we'll divide by 20 minus 10, which is 20 years minus 10 years. So this is over a 10-year period. So then you can calculate this. So 15,011 minus 1,412 gives us 13,599 divided by 10 gives us 1,359.9. And then this is going to be stores per year. So then this is going to tell us that the change in the number of stores was about, 1,360 stores per year from 1997 to 2007. Okay, so this is the change from 1997 to 2007, 20 years after, 10 years after 1987 and 20 years after 1987. There's your growth change. And if you want, you can compare that to the original change in the first 3 years, right? And remember that was like 22.3 stores per year. So if you did 1359.9 divided by 22.3, you would get like 60.98 times more than this first chunk right here. Okay, so that 22.3 represented this first 3-year chunk. And now the first 20-year chunk is 61 times more than that growth rate. So definitely extending. And then we looked at this when I connected those as if I extended them, right? So we looked at that when we were calculating those average rate of change, but we can see that the first one was good for a little while, for the first 5 years or so. The middle one over predicted the first couple years and then significantly under predicted the rest of them. And then looking at just the 10-year rate of change didn't really predict anything very well. In the beginning or after. So how would the average rate of change between 94 and 97 accurately depict how the company was growing in the last 3 years of the data? Is there a single period of time whose average rate of change would well summarize how the company was growing over the 10-year period? So looking at this first question, if we went back to the table and it's talking about from 94 to 97, so that would be wanting us to conduct the average rate of change here. So if we looked, we could do 1412 minus 425 okay, those store differences, and then divided by 3. And if we did that, so subtract the 425 from 1412 and then divide by 3, you get 329 stores per year is what this is saying. So then you could just look at how much these stores actually changed each year. So 677 minus 425 gives us a change of 252 stores. 1015 minus 677 gives us a change in 338 stores. And 1412 minus 1015 gives us a change of 397 stores, all relatively close to this 329 per year, right? So one kind of below, one above, and then the middle one is pretty close. So it does do a pretty good job for those last 3 years. And then, is there a single period of time whose average rate of change would well summarize the growth rate from 1987 to 1997? And not really, because when we looked at this, none of those were great, and there really isn't. Like, if you want to connect these, any two dots, like if we connect the first two, second two, third two, fourth two, fifth two, like that gives you, it's okay for the first 5. We talked about this one. Then this one really isn't predicting very well any of them, right? It's pretty far above those first 6 and pretty far below the next ones, and same for any of these. So none of them do a good job predicting all 10 values, okay? Little chunks of it for sure, okay, but never the full data. All right, in activity 10.3, we're going to analyze another exponential function. You're going to explore the average rate of change for a function. You're going to make a prediction, and then you're going to discuss strategies and reasonings. So you can pause the video and get started on this activity, and then come back when you are finished. Here's a graph that you saw in an earlier lesson. It represents the exponential function P, which models the cost P of T in dollars of producing 1 watt of solar energy from 1977 to 1988, where T is the years since 1977. So we're going to be looking at this graph again. Claire says in the first 5 years between 1977 and 1982, the cost fell by about $12 per year. But in the second 5 years between 83 and 88, the cost fell only about $2. Show that Claire is correct. So let's calculate the average rate of change for each of those domains that she gave us. So we've got this time period, and it fell $12 is what she's saying. So we want to be looking at 1977 represents T equals 0. And 1982 represents T equals 5. So we're going to be looking at, remember, you do the new minus the original. So P of 5 minus P of 0 divided by the time period. Okay, so in this case, 5 minus 0. So we'll look at the graph. So P of 5 is maybe like 19. And P of 0, so at 0, P is at 80. And then 5 minus 0 is 5. So we'll do 19 minus 80 divided by 5. And we get about negative 12.2, right? So that negative means it's decreasing. And then we do get about 12, like Claire suggested. So that checks out. So we showed that one. Then let's show the other interval that she said. So 1983 to 1988, it fell about 2. So 83 is 6 years after 1977, and 1988 is 11 years after 1977. So we'll do P of 11, the new one, minus P of 6, the original, or the starting time period. And then we'll do 11 minus 6 for the years. So P of 11 here is So this is what, 1, 2, 3, 4. So these are counting by fives, 5, 10, 15, 20. So it's a little under 5, so maybe 4. And then P of 6, okay, is a little under 15, so maybe it's 14. And then 11 minus 6 is 5. So 4 minus 14 is negative 10 divided by 5 gives us negative 2. So we do see that it's decreasing by about $2. Number 2 says if the trend continues, will the average decrease in price be more or less in the next 5-year time period? So we looked at this first 5 years, right? So we did 77 to 82. So we looked at what it was decreasing in here. Then we looked at what it was decreasing in the next 5-year period, right? And now we're going to be looking at what would be happening in the next 5-year time period. And it would make sense that it would be less than 2, right, if the trend continues, because from here it was going down over $12 a year. So that was a pretty steep decrease. And then it started flattening out. Now it's only going down by $2 per year. So it would make sense that, yes, if the trend continues, it would be less than $2. Woo, $2 per year. The table gives the values in dollars of a laptop originally priced $1,500 and losing 3/5 of its value every year after purchase. About how much was the average rate of change for that 5-year period? So we would take the final value of $1,536, subtract off the original value in the period we're looking at $1,500, and then we could subtract the years to get the time period. And so when we do this, we get like negative 296 point something dollars. So that's giving us a decrease of about $300 per year. And does that accurately describe what was happening with the laptop's value over those 5 years? And I would argue probably not, right? Because this decrease is $900. So that's a decrease of $900. And then when you get down here, 96 minus 38 is really only about 60, not exactly 60, but approximately. And then 38 minus 15 is really only about a $23 decrease. So it's losing a lot of value in this first year and then not as much value in those final years, okay, at least as far as in dollars per year. So I'd argue probably not. This doesn't do a very great job. And then are there some years where the average rate of change does predict its value well? So, I mean, yes, for this, that right here, it only decreases by about, what's that, 360? So it decreases by about 360 there. So this is about that. We're a little bit more than 300, but not significantly more or less like the other ones are. So yeah, from year 1 to 2, it does an okay job, but definitely not for the whole 5 years. So you should be able to calculate the average rate of change for a function over a specific time period and know how the average rates of change of an exponential function differs from a linear function. If you need to check your understanding of this lesson, you can look at the lesson 10 practice problems and find my video on that where I go over detailed explanations of each problem if you need more help with that. And then you can also try this cool down. And if you're struggling with the cool down, you can ask your teacher for help on that.